introduction to the configuration of the truss and journal bearing, hydrostatic bearing and or hydrostatic journal bearing. So last week we also gave you the some basic configuration for the hydrostatic bearing. So here we have spherical bearing, so, and the conical bearing here as well. And for this one is truss bearing, and here these two are joint bearing. So, and this is a special bearing invented by the author. Okay, but there is no practical application for this kind of bearing because it's very difficult to manufacture this one. So probably you need to have two parts, and this part should be connected to the other part. And, so this is a special configuration for Yates invented by the author. Okay, so for the conical bearing and the spherical bearing, these two bearing types, it can resist the radial direction force and the axial directional force. So for traditional one, you have a truss bearing and a journal bearing. To understand the basic configuration of the truss bearing and journal bearing, it's necessary to understand how you can design a spindle. For example, the milling spindle or grinding spindle. For those kind of spindle, you need to have a combined axial force and also the radial force resistance. Okay. So here is just a basic example for the design parameters for those bearings. For example, for the journal bearing, the arrow is the length of the journal bearing. So we have a journal bearing configuration. Before here, so the arrow means the length of the journal bearing. The diameter is the inner diameter of the journal bearing, or the shaft diameter. Okay. For journal bearing design, usually we design the length equal to the diameter. So that's why when you design your basic journal bearing, this means you need to design the configuration, the length equal to the diameter. So, and also for the load capacity, this is basic parameter for the design. For the annual trust theory also introduced it before. The first hydrostatic theory we give to you is Coulomb trust theory. Okay. So you have the angular read for the trust system. So this is the trust theory. And we can look at it slowly. So for example, this is the transitional configuration for hydrostatic spindle. Okay, you have two truss bearings. This is one truss bearing, and this is one truss bearing, and two joint bearings. Okay, and if you use these basic conical bearing or spherical bearing, truss bearing or joint bearing, you can have a design for the spindle configuration. For example, you can design your spindle with two conical bearings or two spherical, semi-spherical bearings in this case. And here we also have an example with one joint bearing, 1 year bearing, but this is not reasonable, not practical because you never see this kind of product in the market. Okay? So these are the spindles configuration for hydrostatic bearing. This is the traditional one. Two truss bearing, two joint bearing, and also in the spindle design with the two semi-spherical bearing or two conical bearings. And here is the basic parameters for your design. We will discuss this later in the design of the bearing configuration. So, for example, the conical or semi-conical angle is the angle measured from the horizontal direction to the called the semi-conical angles. And, and you know, to manufacture this conical bearing or the spherical bearing is more complicated compared to the traditional truss bearing or joint bearing. For this kind of bearing, you can manufacture in 3-axis milling machine. And for this conical bearing, you need to manufacture this cone angle. So you need to have a 4-axis milling machine. And for this spherical uh, bearing, you need to have a 5-axis machine. So the productional or the production cost for these two spindles will be higher than in traditional spindle. So in the market for the hydrostatic bearing, I would say maybe 70 or 80% of the product are manufactured with the traditional configuration, and only a few of the products were manufactured with conical bearing or spherical bearing in the spindle design. So here are some of the rules found for the parameters in the design. So you should notice for drum bearing, usually we design the drum bearing with length equal to the diameter. And for the annual thrust, usually is 1.25. For the maximum diameter, compare with the minimum diameter. Okay, which means the, this is the maximum diameter, and this is the minimum diameter. Okay. For the traditional spindle, milling spindle or grinding spindle, we usually use the ball bearing to design the support of the spindle. But in our hydrostatic spindle design, we use the hydrostatic bearing instead of the ball bearing. So in the patent document, whether in US patent or Taiwanese patent house, you can search these three types of the hydrostatic bearing spindle on the patent document. There are a lot of different configurations or different special design for the hydrostatic spindle. Okay. You can also find one of the Yates spindle uh, in the patent document designed out by the author of the book. Okay. So let's also look at the truss bearing design. Okay, this is the annual truss bearing, and we arrange multi-reset, which means in this 360-degree configuration, we have 1, 2, 3, 4, 5, 6, 7, 8 resets. And for this also rectangular multi-reset design, we have 4 resets here. Okay. In the hydrostatic bearing design, you need to, if you can, you should, if you can, you should design the multi-reset the bearing head. Because when you have a different film gap in your hydrostatic bearing. If you have a large gap, you will have a low capacity. Okay? You have a multi-recess bearing design. You will have a better low capacity performance hydrostatic bearing. So that's why in our products you can always see this kind of design. Same for the rotary table, hydrostatic rotary table, vertical leg design. We also have a different design strategy. For example, we have a multi-recess in the truss bearing design. So you need to design the individual recess number at least 8 to 10. Okay? But it depends on the size of the spindle or the size of the rotary table. You have a different design strategy. For example, for this is 6, no, the diameter is 5.3 meters diameter, the rotary table. But for smaller rotary table, for example, for this one, I think it's 1.4 meter in diameter. So you have a less recess design. Here you have only 8 recess in this design. And for the slide table, linear slide table is the same. For this one is flow type boring machine. So this can move on the floor. And this linear slideway system or guideway system is designed by the hydrostatic bearing as well. So this is a linear guideway system, for instance. two square rail on the bottom. So you can see the yellow one. The yellow one is hydrostatic bearing pad or hydrostatic bearing reset. So we can look at on the top of the slide there. So in the linear direction, we have one, two, three, four, five, six pads. Okay. On the edge, these two are the smaller regions. In the center, you have the two larger leads for the region. This is the big one. So with the multi-recess design, you can have better resistance for the non-concentric loading. When your loading is not centric to your mass center, which means that some of the weight maybe on some space, some area of the table. So if you have a multi-recess design, you will have a better resistance to the eccentric force for your old piece. So that's why we said that you can offer a better field resistance for the multi-recess. I think there are some of the design rules for that. So you design how many meters you need to have in one direction for linear flywheel system, linear hydrostatic flywheel. So in one direction, you need to have at least two or three resets minimum for the design. And, and then we have some example for the commercial application. For the commercial application, the first one is the hydrostatic bearing under the basic structure of a nuclear facility. We also have some kind of hydrostatic bearing under the observatory. Okay. Here are the example for the grinding machine. So this is the grinding spindle. It's made of traditional hydrostatic bearing, two truss bearing and two journal bearing. In this case. And also for the linear guideway system, it's also made by hydrostatic. So this is one of the pictures. So show you the rotary table designed by the German company named Zollner. Okay. So you have truss bearing two fluid trust bearing and four fluid trust bearing, and you have also four journal recess, four recess in your journal bearing. So the bearing size here is 500 millimeters in diameter. So for this 500 millimeters in diameter, you can resist the loading of the 3,000 kilogram. So it means not 3,000, no. It's a 50 ton loading. So this is typical. So usually if you have a machine tool or rotary table, you need to carry the loading larger than 5 tons or 10 tons. Usually they will make the rotary table by the hydrostatic table. Okay. And another example is the air bearing spindle for the PCB printed circuit board for the computer. Okay. Because they need to drill a small holes in order to connect the different circuits in your PCB board. So you need to drill a very small hole in very high speed. So Westwind is a famous UK company specialized in the air bearing spindle, especially for the high rotational speed. So in this case, Westwind can provide the spindle, the RPM speed range can be starting from the 20,000 to 200,000 RPM. So if you look at the website from this company, now for the latest product, the speed range can be raised to the 500,000 RPM. And this is the typical for the air bearing. Price pressure will be smaller than 6 bar. In this case, it's 5.6 bar. So this is a typical commercial product for hydrostatic. And for the manufacturing or construction of the hydrostatic bearing, usually you need to fabricate or manufacture the very precise part with very small tolerance. So that for these hole, you need to operate with the film gap thickness, maybe 20 or 15 micrometer. So the production precision for the manufactured part should be very precise in the dimension. Okay. Here is an example for the four-recess hydrostatic joint bearing So you can look at one, two, three, set here. After operating 10 years in service. Okay. So usually, if you can design a good hydrostatic bearing, there's no touch for the bearing part. So it operates separated by the fluid, either oil or gas. So free of the touching, so there's no way for the machine part. And so usually can operate a very long service life. So one example of the German lathe company, it offers the turning machine designed by the hydrostatic German bearing, guarantee 5 years for the hydrostatic bearing, guarantee 5 years service life for hydrostatic bearing. There will be no way if you operate properly for your hydrostatic bearing. So these are also some of the parts for the restrictor, not restrictor in this case. This is just for demonstration for the John bearing design is not restrictor. Usually the material for the bearing is made of tooling steel, okay, most of the case. And we also will discuss later in chapter 2 or chapter 3. So you can look at the some description for the material selection in the text. Okay. So most of the emphasis will be put on the hydrostatic bearing. And we also be some description for the air bearing. So for the air bearing, or for the aerostatic bearing, usually applied in semiconductor or clean room precision machine tool. Because in semiconductor industry, you cannot use the hydrostatic bearing in your cleaning room because you will have a risk. If you use oil hydrostatic bearing, you will have a risk your lubricant during the leakage will contaminate your cleaning room. So that's why it's forbidden to use oil hydrostatic bearing in semiconductor industry. So always in semiconductor industry, you use aerostatic bearing instead of the hydrostatic bearing. But one, maybe we can talk later because for hydrostatic bearing, if you are interested, you can look at the actual bearing or aerostatic bearing. Actually, there are two types of the air bearing. For the traditional one, you have a very flat design, plus restricted design. There are also a new type of the air bearing called the porous air bearing. In this case, you don't have any restriction. So in this course, we will discuss the traditional. There are also different type of air bearing called the porous air bearing. This kind of bearing is made of a porous material. So the material, porous material inherently it has some small pores in the material. It can behave like a restrictor. So in this case, you don't need to install extra restrictor on the material. But the difficulty is how you can manufacture this porous material homogeneously in different shapes for your product. This is the know-how. Okay. And for the air bearing we discuss here, we always discuss the bearing pen design plus the restrictor design. And for this one, the supply pressure usually smaller than 6 bar. And for the porous material, porous air bearing usually can supply the pressure bigger than 6 bar. Okay. So in some applications, people will design the air bearing using the porous material. This is another story, another design background for the porous air bearing design. So it's not in the scope of this course. Because this kind of a material was developed in 1992. It's getting popular, getting popular in the recent years. 所以气机压轴承其实有分两块，一个是传统气机压轴承，就是我们讲你要去设计油枪，应该讲油枪的形状来设计节油器。另外一种就是叫多孔性气机压轴承。多孔性气压轴承就是它其实要靠一些模具去做出多孔性的材料。 然后你其实可以打的工期可以大一点。So the low capacity, this kind of overlay bearing is bigger than, is better than the traditional air bearing. So here are some of the advantages for the air bearing, aerostatic bearing, especially you need to operate at very high speeds or in a very small run out. Then you need to choose your system with aerostatic bearing instead of hydrostatic bearing. Because for hydrostatic bearing, if you operate the rotational speed that are bigger than 3,000 RPM, you would generate very high or very uh, high temperature in your lubricant. So you will have a problem for the thermal deformation for the system. So in that case, if you need to run very high speed, for example, for our PCB air speed, you need to run in 500,000 RPM, then you need to use air bearing instead of a hydrostatic bearing. Maybe 10 years ago, I went to the conference in the United States. One consultant company in the United States, it presents a hydrostatic spindle can run, I think it's 12,000 RPM, and they need to have a facility, I would say, occupied nearly half of the classroom to cool down the lubricant. So if you run in a very high speed for the oil hydrostatic spindle, it generates tremendous heat, should be cooled down. So it's not really practical to use the hydrostatic bearing in very high speed. Yeah. So for the aerostatic bearing, or sometimes we call name is get lubricated bearing. It can use the gases such as nitrogen. Usually, it's in some nuclear facility they will use this one. So it's not just only just not the air only. You can use different type of gases. But of course, for this kind of nitrogen, you need to have some recirculation system to collect them. Okay. That would put also extra cost for your system. Right. Raw material. So usually for the traditional air bearing, it operates which is a supply pressure of 4 to 6 bar maximum. Okay. If you supply your air higher than 6 bar, you are encounter the problem of pneumatical hemorrhage ability most of the time. So this is a major problem for that. So that's why when you need to have a higher load capacity for your air bearing, people will switch to the porous air bearing instead of the traditional air bearing. So now we look at the second chapter for the basic flow theory. So in this chapter, we will introducing the basic theoretical background for the hydrostatic bearing. So by introducing first the viscosity object we look at, and also introducing some of the density and some of the units for your different systems. And for the air bearing, you need to understand the concept of compressibility. Okay, so you your supply air, your supply pressure is higher than 6 bar because for the air it's compressible, so you have a problem when you pump in a higher pressure of your air, but your the performance or the low capacity of your due to the compressibility of your air. Okay. So for the bearing theory, we will introduce you the viscosity flow between two parallel plates. Okay. And then we will derive some of the basic formula for the two-dimensional flow, okay, for the hydrostatic bearing. And we also will introduce you some of the concepts for the flow through the restrictors. Okay. And we have some terminology for hydrostatic bearing. For example, the pressure ratio. Okay. Pressure ratio is the recent ratio divided by the supply pressure or the pressure ratio. Okay. And we also want to know for the bearing performance, the most important one is the low carrying capacity. So with the design bearing at how big the loading you can carry for the bearing head. Okay. And most of the theory we will introduce you with oil hydrostatic bearing theory. And then in the end, we will give you some of the formula for the air bearing. So throughout the textbook or throughout this book, most of the theory or formulas derived in this book are based on the hydrostatic bearing. And for the air bearings, the author only gives some of the final results. Okay, so and so this is the content of the second chapter for the basic flow theory. Okay, and I will take a break for 10 minutes. Okay. So we start to introduce you the theoretical background for the hydrostatic bearing. So we have lubricant flow and we have grouping force in very small gap. And with a high supply pressure and this pressure distribution across the bearing surface can sustain extra loading for that. So, and for hydrostatic bearing, we have the flow rate through the restrictor and through the hydrostatic bearing. So therefore, here in this chapter, we will derive some of the basic formulas to describe the flow capacity, flow rate, and recess pressure. Okay. And what should be mentioned is that the lubricant used in the hydrostatic bearing is the Newtonian lubricant, which means the fluid property will be governed by the pressure and also the viscosity of the lubricant. So we will give you the flow rate formula in this case. And also for the compressibility of the air bearing, we also will discuss the structure property for that. Okay. So first, to introduce you to the Newtonian fluid, is this is a formula called the Newton's law of viscosity. So the shear stress for this fluid will be governed by the viscosity of the lubricant multiplied by the velocity of the lubricant divided by the film thickness of the lubricant. Okay, so if you follow the formula of this formula, the lubricant is called the Newtonian lubricant. So for the lubricant we use the hydrostatic bearing, such as the oil or water, they all follow this formula. So we call this kind of lubricant is Newtonian lubricant. So in that case, this is the shear stress. So the shear force will be the shear stress multiplied by the bearing and area. Okay? So this is the bearing and area. AS. The shear surface area. So this is the shear friction force in this case. So here we have a definition for the viscosity. Viscosity is the fluid related to the shear stress to the rate of the shear. So which means this one. This one is viscosity. So here is the velocity distribution for the lubricant. So in the graph, it's fixed, it's stationary. So which means the velocity of the graph is zero because it's fixed. So and these these are the film thickness of the lubricant H. Okay, on the top, the velocity is u, moving velocity for the lubricant of u. On the bottom is zero. So here is the velocity distribution for the film thickness of the lubricant. So to give you the definition for Newtonian lubricant, it will be viscosity following Newton's law of viscosity. The lubricant is called the Newtonian lubricant. Okay. The viscosity of the Newtonian fluid is constant with the shear rate. Which means that in viscosity is some relationship with the shear stress and also the velocity distribution divided by the shell thickness. Okay. So here also give you the some example for the Newtonian fluid water air, simple mineral oil. So mineral oil is an oil refined from the fossil oil. Okay. So here is the unit, SI unit for that, for the viscosity. And we also give you the definition for kinematic viscosity. It's related to the dynamic viscosity by the oil density. So with the viscosity we call here is dynamic viscosity. If this one divided by the lubricant density is called the kinetic viscosity. We also know the viscosity will change by the effect of the temperature rise. Okay. So this is the relationship between them. Okay. So the effective temperature, so the initial one plus the 0.5 multiplied by delta T. Delta T is the maximum theoretical temperature one based on the 100% of the heat dissipated by convection into the lubricant. Okay. This is the assumption for that. So the temperature change delta T. Okay. This is the initial temperature, the final temperature, or effective temperature. This is one of the relationships. So when you use the lubricant in your hydrostatic bearing, if the operating temperature is getting higher, then your viscosity of the oil will decrease. Decrease. These are the another estimation for the effective temperature. And in this case, it's not point 0.5 to point 0.8. Okay. So this is based on the assumption T. Delta T is based on the 60% of the heat dissipated by convection. So if the temperature rises high, viscosity in the building will be different from the viscosity in the control device. So in this case, this this is the estimation. This method will give you almost the same effect temperature, which is based on the viscosity, but reduce the temperature by slightly. Yeah. Here are some examples for the typical values of dynamic viscosity. So we have different fluid type, air, water, water in different temperature. machine oil. Okay, the basic oil, like one in low temperature, 15.6 Celsius. Another one is machine oil in 37.8 Celsius. So the dynamic viscosity here, we can look at that. So for the air, viscosity, dynamic viscosity is very small, 0.0183. And for the oil, you have 113.8. So the viscosity of the oil compared to the air, the 100,000 times bigger than the air viscosity. So I look at this table, you can also look at for different temperature for the water, 20 degree and 30 degree, the viscosity is lower than 20 degree. Okay. And for the lubricant oil, 15 degree and 37 degree, so the lubricant viscosity is reduced from 113 to 34. Okay. So the higher the temperature, the lower the lubricant viscosity. This is important. So when you operate at very high temperature, once the temperature is right, the flow capacity for your hydrostatic bearing will be reduced in this case because the low capacity of the hydrostatic bearing is proportional to the viscosity of the lubricant. Okay? So you operate in higher temperature, low capacity of the hydrostatic bearing will be reduced. So that's why most of the case for hydrostatic bearing, if you need to be operated continuously, you need to have a cooling system in your pressure supply system to maintain the constant temperature of your lubricant so that your low capacity will not be reduced.所以这就是为什么我们操作这个静压轴承的话，如果温度升高的话，其实它的油的粘度会降低，油的粘度降低，它的轴承的承载力就会降低。一般静压轴承不管是主轴或工作台，它的供油系统都会加一个冷冻机，让我们这个润滑油维持在固定的温度。Okay, this is some of the discussion for the density of some UV. So this is the comparison of the density for some material, air, water, machine, oil, like 20 degree, machine oil, like 100 degree. So the density also will be reduced in this case. So here is the measurement for the compressibility. So liquid is assumed to be incompressible in for most configurations. In our case, for the hydrostatic bearing, if the supply pressure lower than the 80 bar, this is a rule of thumb. So if we operate less than 80 bar, it's assumed incompressible for hydrostatic bearing. Or for the air, I would say light will be in the same side, usually. For the air purity design, if you don't have any recess, if you operate less than 5 bar, usually we will assume it's incompressible. So this is very important. So because when you are designing the hydrostatic bearing, you can choose the parameter as you wish, and then you need to be careful to choose the supply pressure lower than the number. Because once you choose a higher supply pressure, then the oil becomes compressible, and then you need to choose the oil pipe in different categories. That may increase your cost for your oil pipe. Okay? 所以这个是不可压缩的话，供油的话，大概一斤压的轴承的话，大概88以下的话，都是把它当成是不可压缩。气气压大概是5%以下，但是气气压有一个前提的话，通常它是不能设计那个强制气气压轴承。你如果要选你的供油压力或供给的压力超过这个限制的话，你所有的胖虎啊线都要选高压元件，成本可能会增加至少50%以上。If you operate the supply pressure higher than the number, then you need to choose your pump, your oil pipe in different pressure categories, so that may increase your cost. 这个是我们一般这样，因为我们讲设计啊，设计的话是所有的参数你就可以选，你让人家选这个比较 one get so this is a formula to analyze your compatibility. It's called the Buck modulus of the elasticity. This is the change of the volume. We have a one Buck modulus constant here, K. For the design of the air barrier, you should be careful for this compatibility. For the hydrostatic bearing, I would say usually no problem. You can assume the liquid lubricant is incompressible. So this is the compressibility of the gas. This is the formula for the gas. The general gas law, 气体的方程式，理想气体的方程式。So for the air bearing, you can use this formula as well. So P is the absolute gas pressure. V is the volume per unit mass. C is the absolute temperature. R is the constant. 理想气体的常数。So this will be used in the air bearing. For the polytropic pressure change, we can use this formula. So the pressure change will also cause the temperature rise. So this is another formula to estimate temperature. For the calculation of the air bearing, is more complicated than the hydrostatic bearing. For theoretical calculation, more complicated. Right. So next, we want to know the flow between two parallel plates. So why we need to derive the equation for the discuss flow between two parallel plates. Because the same situation like your bearing, when we can go back to the chapter 1. when you look at the floor between these two gaps, like exactly like the same parallel plate floor, discuss floor between two parallel plates. Okay, so same. So that's why we use need to derive the equation for that. So discuss flow. So the Newtonian look at flow between these two plates. So you can assume this is the trust bearing and so this is a fixed flow. Yeah. And here we have a lubricant. It's a pressure induced flow. So because we use the pressure supply system to pump in the lubricant into the bearing surface. And this one. So the pipe ends are pumped in here. So the flow moves from this point to the outside of the bearing. So when you look at this small interval, exactly the same like this one. Okay? So pump supply a lubricant into this bearing surface. So the lubricant is moved in this direction. So this is the pressure, no, velocity distribution for the lubricant. So because these two plates, we, we first consider the most simple one. Simplest case, this one is both these two plates are fixed. Okay, so the velocity of this point is zero. Velocity in this above that point is also zero. And the velocity distribution here. And here is we take one small element, lubricant element. We look at the three party diagram for this small element. So it's pressure induced flow because your pressure difference induce flow to move. Okay? So this is exactly the same partial differential equation for fluid mechanics. Okay? So this rectangular element, we have some force acting on different surfaces. So we calculate force balance for this small element. For this horizontal direction, you take this direction in the x direction. This one is positive direction. So in this case, the force in this direction multiplied by the thickness of the element is called the v. This is the x direction, y direction, z direction is this direction. Thickness for this one is v. So you have this force balance, and this is the force. right hand side. And here is the force on the bottom, the shear strength multiplied by the net for each element, delta x. The thickness in the z direction is on the top is a partial differential equation in the y direction. Only these four forces can be balanced equal to zero. And you will have our flow equation on that. Okay. So for this one, you can summarize it to this one. And you substitute the shear stress by this Newtonian fluid equation into this tau. Okay. And then you have you can also have the boundary condition. Boundary condition is velocity. The velocity in the y direction, the change is zero at center. Center is y equals to half of h. Okay. And also the velocity on the bottom on the top is zero. So we can have this. This is the velocity equation for this significant hydrostatic between these parallel planes. Get this one. This exactly is the pressure distribution. So this is the velocity. We know the velocity. We know the cross-section area of the bearing head. This parallel plane, the cross-section. You multiply the velocity with the cross-section area. You have the flow rate, volumetric flow rate for its lubricant. You multiply with the density, you have mass flow rate. This is the flow rate between these parallel planes. This formula can apply both fluid, no, liquid and gases, which means this volume flow rate and mass flow rate equation can be used for the both hydrostatic bearing and aerostatic bearing. It's the same discuss flow between the parallel planes. So give you the first equation for your balance flow rate for the one bearing. So if you have several bearings, you can calculate individually and adding together, right? So this is the equation for that. So this is other differential equation. How you solve it? So for the practical bearing design, you can substitute them into different dimensions. Okay? So for instance, radial gradient, dt divided by dx can be used this one. So this is the liquid flow we use. And this is for the gas flow from the air bearing. So most of the formula was derived from the hypostatic this case, and then give the aerostatic bearing formula as a result of the process. So in this case, is that the first case is the movement of the lubricant is by gradual difference because we pump in lubricant into the surface. So it's a flow movement induced by the pressure. Okay? So we assume these two plates are fixed, fixed. Okay? It's not moving. And the next case, the top plate will move. Okay? It's like the our so this is linear gyrate part. Okay? So and this movement on the fixed rail. Okay, so this one is moving. It's more like example we show you the top surface is moving. The fixed rail is the on the bottom of the rail is fixed. Only the top and in between lubricant oil. Actually, so consider the second case, velocity induced flow. So remove the top plate because of the lubricant is viscous lubricant. So it will be plate. So this top plate movement will induce the velocity into your lubricant. So this is the second case we need to consider, velocity induced flow. So for this, in this case, we have on the bottom, the velocity is zero. On the top, the velocity is u. For average, the velocity u equal to u divided by 2. This is the average velocity in the center. The velocity multiplied by the area of this plate, the height and the width. The height is h. The width in this z direction is v. So flow rate in this case is this one. Or you can think of the average velocity. You can cut this one and move this one to here. So and this one is the volume flow rate. Okay. For mass flow rate, usually we use m cost, but this textbook m is used mass flow rate. Okay. So mass flow rate equal to the volume flow rate multiplied by the density of the fluid. So this is another formula for this circular area. Circular So this is to calculate first. Yes. To calculate the simplest one, the circular area. You can calculate the volume flow rate Q by the formula. So here is the final formula you can substitute into your hydrostatic bearing. For the liquid one means the hydrostatic bearing. For the gas one is air bearing. Okay? And you can see you have some symbol here, P bar. Just gives you a better look for the formula. So P equal to this. So this one is for the gas. It's the bearing. It's the pet. It's the circular bearing. For the air bearing. We use the gas one. It's the circular bearing. It's for the oil hydrostatic bearing. You use the liquid one. This one and this one. The air bearing. So we have two cases. One is the pressure-induced flow. Both plates are fixed. And the second one is the velocity-induced flow. The bottom one is fixed and the top plate is moving with the speed of u. So we can combine these two effects together. So for the air bearing, or for the hydrostatic bearing, the linear table will move in a constant speed. Okay, so in practical one, it could be fixed or it could be moving, rotating. So we need to have combined effect for this one. So the velocity distribution could be this formula. So these are the velocity distribution combined velocity and pressure induced flow. We also have some two boundary conditions. So we are second order equation. So we should have some two boundary conditions to solve this pyramid. So we have some different cases. So this is a slab area. And this is the final Reynolds equation in two dimensions. Okay. So if you're, the general form for two-dimensional incompressible can be either compressible or incompressible. These are two-dimensional Reynolds equation for non-parallel thin film can be used with this equation. If the top plate is fixed, so the u equal to zero, so the right hand side will be zero. This one is simplest one. So final equation. We have only for hydrostatic bearing is not so difficult. We have only these formula. Okay. Only the chapter 2 will have some formula to calculate the velocity distribution and also calculate the flow rate, to calculate the low force, low capacity thickness can be. So we have some cases. If you combine the restrictor here, design here, so we have the supply pressure P up and downstream to the reset. You have supply. You have a reset pressure PR. So from the supply pressure is PS. Okay. And in between you will have some a device called the restrictor. Okay. So and then we have a mass flow rate. So the mass gets into the restrictor should equal to the mass into the barrier. So this is a conservative equation of mass here. The mass flow rate for to the restrictor should be equal to the mass flow rate to the barrier. Because you have only one way to get into the barrier. The mass flow rate passing through the restrictor should be the mass flow rate getting out the barrier. Sum of the restrictor flow should be equal to the total flow out of the barrier. So now we have a connection between the flow in the barrier and the flow in the restrictor. Here we have this equation. Uh, this is the mass flow rate. Mass flow rate equal to the volume flow rate multiplied by the density. For this short distance of the flow, the density will assume the density remain constant from the upstream to the downstream density equal. So this may be changed to this one because the density flow is constant. Right? So from this 2.18, you can change it to this one. The volume flow rate through the restrictor equal to the volume flow rate out of the barrier. 这就是能量走进去的质量要等于出来的质量。进去这个节流器的要等于出来轴承出来，因为你的质量或者是你的质量不会留存在中间，气体会等出。Okay. And for different type of restrictor, you can derive the formula individually. 所以对不同的节流器的话，其实你可以把它的公式每个都求出来。So this one is a capillary restrictor. For For the capillary restrictor, it's the laminar flow restrictor. So we should prevent the Reynolds number for the flow velocity to ensure it's in laminar flow. Okay? So this is a formula you can calculate or estimate the Reynolds number. 以雷诺数的部分，我们可以去估算它的雷诺数。雷诺数小于2000，so the Reynolds number smaller than 2000 will be the laminar flow. So this is the number you can check this is correct for the Reynolds number. So the Reynolds number less than 2000 for laminar flow. For capillary restrictor, it's a laminar flow restrictor. So we can double check the Reynolds number, see if it is really 毛细管节流器主要是层流的节流器，我们可以计算那个雷诺数，这个是管流，毛细管就是在子宫管里面流动的那个速度，我们可以去算它的雷诺数，就可以知道是不是真的是层流。它如果是小于2000，so this is the capillary restrictor, and we have also different types. Large restrictor, this is formula. And you see for the air bearing one, usually it's more complicated. For theoretical analysis, air bearing is more complicated compared to hydrostatic bearing. So this is 狭缝节流器 large restrictor. And we also have two different types of orifice restrictor. The first one is a simple orifice. Another one is called the annular orifice. Annular orifice is easy to manufacture. You just using a drill to drill a hole. This is use of the orifice restrictor. And for this simple orifice is that we show you the video. You can buy this this kind of restrictor from some manufacturer. You can also try in eBay. Okay. Type in the orifice, simple orifice. You can buy it by kilo. 这个是有专门的人在做这个节流器，小孔节流器，他们其实是用那个粉末眼镜做。如果在低倍里面，对美国的话是可以论公斤买。那像这个圆形的小孔，就是我们直接就是拿我们的钻尾去钻，通常这个都很小，大概是两米米、2、3米米以下钻一个孔，那就是节流器，小孔节流器。所以氢气压轴承、空气轴承很多人都是这样做。So this is the formula you can calculate the flow rate downstream in downstream flow rate here. The Olympic restricted by using this formula. Cp is a kind of discharge coefficient. Usually this one should be examined by experiment. Okay? But most of the case, you can Cp is the discharge coefficient. This should be verified by the experiment. But for the majority, 所以这个叫做那个 for the majority, they are lying between the most of the case for the Olympic. People usually verify this discharge coefficient by experiment. But most of the case, the city will lie between 0.5 to 0.6. So you see, for here, the random number is 1 million. Okay, so it's greater than 2,000. So this means the restrictor, the oasis, is a turbulent flow restrictor. 所以它的雷诺数的话是在多少？100万，所以它大于2000，所以是在稳流，或是有些现在中国大陆都用宽点，就是稳流。所以小孔节流器是稳流的节流器。So Olympic restrictor is a turbulent flow restrictor. Okay. But if you want to calculate the flow rate in the restrictor, you can use this formula. The A naught here, A naught is here. The D naught is the diameter. No, the area is passage. Okay. So for the air bearing, it's more complicated. Okay. So the flow rate here using this formula. Okay. From theoretical point of view, it's more topic. So it gives you the formula to estimate the flow rates with different with the design of different restrictor. Yeah. So we have also some discussion for that. So it discuss how the discharge coefficient will change between different range. So this is another formula from the estimation of the mass flow rate for air, oxygen, nitrogen. Using this formula. I mean, with the bearing. So this is the mthought, the mthought with the restrictor. Remember that we calculate this one is between two parallel plates. So it's the flow rate in the bearing or outside the bearing. So, so the full plate. So this is the flow rate outside the bearing. Okay. And now we'll give you this formula here. We know the continuity equation. So the mass flow rate into the restrictor must equal to the mass flow rate outside the bearing. So we already know this one. Now we calculate mass flow rate in different type of restrictor. Okay. So first we give you capillary restrictor. Q is liquid gas. We give you the volume flow rate in liquid for the slug restrictor. We give you this volume flow rate for liquid orifice restrictor. And this is orifice restrictor for air bearing. So this is also for the gas bearing, not just air bearing. You can apply to the oxygen, nitrogen, 氧气或者氮气都可以，是一般化。Right? So then we have probably outside the bearing was equal to the bearing, or inside the restrictor equal to the bearing. So then we have two equations, and we can solve the design process. To go back here, so we have several discussions, especially for the air bearing. Okay. So typical the or if it's discharge coefficient. So most of the experimental research was done in 70 or 80 to give you some of the reference number for discharge coefficient. This is the KB factor, that's a KB for air flow through an orifice. So far, any questions for that? I think there are two different books you can have detailed formula verification for the air bearing.吸进压轴承的部分，空气轴承的部分，我们这边就是直接把结果打出来，没有去推导它，但是有几本书是可以查得到。In the end of the chapter 2, you will have some reference with yeah. So most of the formula for the gas bearing or air bearing was taken from this book, Gross, 1962. So most of the theoretical derivation for the air bearing was done or were done in the 60s. There's another book from Romanian professor. I don't know if there is a book here. No, I didn't see the reference book. But for the formula, most of them are taken from this one, Gross. Okay. Gas film duplication. This one is American professor. 压投资的部分，你可以去参考这一本书。This book is one of the two important books for the air bearing. So you can borrow from the library. Not in our university, but in Chengkong University or Zhongshan University. 中山或者是成大一定可以借得到。早期做那个气压轴承的话，都会去参考这一本书。You can read some of the text for discussion for the air bearings, especially for the orifice restricted design. Okay. You need to read some of the background there. Okay. So, and we don't have enough time to introduce the recent ratio and pressure ratio. Okay, so far, is there any questions? 有没有去印书啊 Have you printed out your textbook? It's better you print out your textbook and take with you to follow the lecture easier. Okay. Chapter 2 is only the only chapter for the theoretical part of the theory design. Not so difficult. 第二章的话，大概就只有气压轴承，大概就只介绍这一章，就这个部分。其实也没有用到太 It's not so complicated Reynolds equation. It's just a two-dimensional Reynolds equation. 只是二维的联络方式写，而且是个特例，所以基本上不会太困难。如果是讲介绍三维的流动的话，就会比较困难。所以可能要去看一看。So you should read the text. Okay, because some of the description you should read it in detail in order to understand theoretical development for the hydrostatic theory. So most of the description in the book is about the hydrostatic theory. It's nothing about the air variable. Okay? So when you look at the formula, it's just they put it in the final stage, just give you the get bearing. Okay, for the derivation is only for the hydrostatic bearing, not for the air bearing. So air bearing is just purely taken from the growth book. 所以我们这本书是完全没有讨论气机压流动层的推导，它是直接把结果贴出来。有没有什么问题？没有问题，我们今天讲下一个。We should stop here if you don't have any question. 理论的部分就只有第二章。